RAW-point TAMS, because visual quality is more than just waviness. Our today's speaker is Christian Dietz, for 9 years manager application technology, color and appearance at Konica Minolta Sensing Europe. At this point, I would like to highlight Mr. Dietz's mandates that make him a true expert in the field of color and appearance for automotive applications. Mr. Dietz is chairman of the DIN Standards Committee, Colorimetry, FNF2 and DIN Advisory Board Color. He's member of the VDA Working Group Appearance. He's deputy chairman of the DIN Standards Committee, Color Tolerances in Automotive Paint, and lecturer for color and appearance at the Technical University of Rosenheim. Please feel free to ask your questions during and after the webinar by typing your question in the appropriate field. If you have slide-specific questions, please do not forget to mention the according page number. All questions will be answered after the presentation by Mr. Dietz. As you can already see, there's already a PDF of the presentation that you can download. I'm now pleased to hand over my word to Mr. Dietz. Mr. Dietz, are you ready?
Yes, thank you very much. So, ladies and gentlemen, welcome to today's webinar, RAW-point TAMS, with the title Because Visual Quality is More Than Just Waviness. We have a very tight agenda that I would like to share with you before we start. We will have a little history of the RAW-point TAMS, explained where does the instrument come from. We will have a look inside the RAW-point TAMS, how is it built, what technology is inside. Then we will have a look at the different measurement modes the instrument supports, which are namely the clear coat mode for high gloss surfaces. We have E-coat and raw material modes we will have a look at, plus optical roughness according to ISO standards. And I will give you an outlook about the TAMS project and a summary of it all. Some of you might have already heard some of the topics like the clear coat mode, and some are brand new like the electrocoat and raw material mode. As Mrs. Bucchieri mentioned, please feel free to state your questions into the chat after the presentation or during the presentation. So let's have a look at the history of RAW-point TAMS. RAW-point TAMS is the result, the outcome of a project that took more than 6 years now and was started between RAW-point Instruments Limited, Volkswagen AG and Audi AG. You might ask yourself at that point why Konica Minolta is giving the webinar if the instrument is built by RAW-point Instruments, and the answer is that Konica Minolta Sensing took over as the exclusive global sales partner for RAW-point TAMS, and as for such, we are an OEM partner of RAW-point Instruments. So how was the project started? When it began in 2014, there was a certain status quo at Volkswagen, which was that were and still are well-established internal tools to capture the surface waviness of a surface that gave good enough results for most tasks, but unfortunately not always matched the visual impression. As you can see down here, for example, we have several surfaces explaining the surface finish between the door and the rear, while there are some surface states where you can say these are ideal or they are harmonious. Sometimes you will find measurements that are inside the tolerances but not matching the visual impression, and so to say are not harmonious. So it all is about quality of the final appearance of a surface, and the established devices were only usable on glossy surfaces. Matte surfaces like E-coat or raw material could not be assessed or had several flaws to deal with in that regard. And as well, due to the scanning movement of those established devices, edges, the outer rims, for example, of a door could not be analyzed. The goals that the project was started with was to have an image-based measurement device, so not to move an instrument across the surface, but simply place and take a measurement in order to avoid surface marks, and also be able to measure and the most outlying edges and characterize surfaces well. It was important to mirror the perception of the auditors and the impression that a customer has when he's going to the showroom to buy a car, to see the same perception as the customer. So it is needed to have a traffic light system persisting of ideally one value only, saying it is good or not acceptable. As we have seen before, there are some parts where the appearance does not match. So it's one goal to have clear quality information for a harmonious appearance. And also very important, not to have a device that is again only usable at one point of the production, but offers consistent use in all intermediate steps of production, starting at the very beginning of raw materials up to the final finish. So how can a device be made? How was the TAMS device made? It all was based on more than 400 panels of very different visual appearance and colors that were evaluated and ranked by auditors, not only of Volkswagen and their suppliers, but also every time accompanied by RoPoint to understand the process and the perception that takes place. While accompanied by these rankings, more than 5,000 measurements were taken during visual evaluation in the production and in the lab. And based on all this data achieved, algorithms were developed by RoPoint and its partners from Volkswagen and Audi AG based on established image analyzing technology. And the result of that project is the RoPoint TAMS that you can see down here from all sides. It's a portable, handy, small device that is image-based, means it's static and using image projection and image analyzing, and mimics the visual perception of the auditors and the customers. It offers improved parameters to control the appearance quality of a car or parts, and due to its mimicking of visual perception has a much higher agreement with that impression, which is essential not only for quality control in the production, but for the overall process. And after successfully testing the TAMS, it will now be part of VW quality specifications and procedures. So as we said, it's an image-based device, but how does it look? So if we take a look at the casing of the TAMS and take away the case, at first we see the control panel, the top, where we have a capacitive touch display and interface. In the inside, we have a CCD camera sensor, plus an internal display and an autofocus system, which I will talk about a bit later. We have an SD card reader for memory and for data transport, as well as an RFID module for non-contact information pickup, if that is supported by the line, for example, removable and rechargeable batteries, as well as pressure-sensitive auto measurement sensors at the bottom. One of the main tasks that we had was to say, what is happening if somebody is watching a surface? So let's say we are looking at a reflective surface, what is happening? And what the eye is subconsciously doing, it changes the focus 2 times, means you go to arm length normally and take a very close-up look on the surface to perceive textures, defects, and small wavinesses. While you step back a bit, like a customer is doing in the showroom, so you have more than, let's say, 1 to 1.5 meter distance to watch a surface, and then the eye is more switching on the environment to see reflected images and the distortion of these images. Subconsciously happening as well is that you normally tend to move your head, you look at the complete car body, so the eye is moving across the surface, and this natural action increases the perception of waviness and other distortions on the surface and transforms this visual sensation into sensations of quality and harmony, or more simply, I like it or I don't. In principle, this is what each of us is doing when watching or looking at something. When we say the RoPoint TAMS measures like the IC, what does it mean? It means that we have a CCD sensor, as mentioned, that follows the same principle as the human eye, assisted by a dual focus system. So the internal camera grabs reflected images that are projected by an internal display. I'm speaking a bit later in the next slide. and in the second focuses on the reflected display image. This is the same principle as we talked about what the eye is doing. When we take a look on the GUI of the touch interface of the TAMS, we have the same display on top as we have on the inside. So both displays are similar, and this allows for very fine projections on the surface. Those images that are projected are mainly patterns, black and white patterns or lines that we call, or will call now, test fringes. And if you wonder what these test fringes look like, I can give you some examples that are real reflections from a real mirror. So all these pictures that you see here are in fact live pictures taken with the TAMS. As the TAMS is an image-based device, it's possible to make, let's say, a photograph of a certain state of the surface during the measurement, so you can export all of these photos. The data analyzed by projecting those test fringes, picking them up by the camera, are analyzed then, as said, by using well-established image analyzing technologies or algorithms, which are namely the optical transfer function, line deformation analysis, and phase measuring deflectometry. What is hidden behind those terms, for those who are not very familiar with it, I will explain a bit further on them when needed. But measuring something is only one part of the game. In order to really measure like the eye sees, the algorithms that are derived by using these analysis techniques needed to be correlated to human perception. And this was done by using human perception trials made at Volkswagen and Audi to calculate surface properties. One side note is, as said, that all measurements that the TAMS takes are saved on the SD card, and that SD card reader in the TAMS also supports the Flash Air Wi-Fi SD technology, so it's also possible to use Wi-Fi communication with the device to get data out of it. Not only values, data numerics are exported, but also complete camera pictures, pre-calculated graphs, and surface maps according to the modus setup. When we speak about measurement modes, what is hidden behind that term? So let's talk a bit about the texture of a surface or the surface property. Some may also call that orange peel or whatever appears to the eye. And these textures, these parameters, these properties are inherent in the paint process and can come from any intermediate step or the substrate quality, the paint formulation itself, or anything. So we can discern 4 steps. Let's say we have the raw materials to start with, the body manufacturing where the raw materials are stamped and molded, body preparation like e-coat and fillers, plus body painting, base coat and top coat. The important thing is, as you remember the goals, that the RoPoint TAMS is capable of measuring in any of these process steps and delivers data that are important to optimize each of these steps. Let's start with the clear coat mode, or the mode that we use for base coats and top coats in the body painting. What you see here is a relative screen of the TAMS where you have exactly the same impression as you would have when you measure a surface in clear coat mode. So you see a couple of values, and namely these are what we call the expert parameters, which are used for diagnosis in the painting process to improve some processes and the outcome of it, plus the so-called management parameters, which are used to benchmark paint quality and harmony and make it easily accessible and understandable when comparing, for example, parts, surfaces, or complete cars. Let's have a look at them in detail. When we talk about expert parameters, we start with what we see on the left side under result, the C. And C is a unit that is ranked from 0 to 100 and is called contrast. Contrast is what is directly related to the absorption or reflectance, whatever you want to call it, from the paint color itself. So if we take a look at a surface and the surface is colored, you can have metallics or white surfaces where you can not really see a reflection. And this is what contrast stands for. It's not as, do I like the reflection? Is it a very nice reflection or whatever? It is simply the fact, can I see a reflection and can I see it clearly and nicely? Or do I really need to look more strongly at it in order to see the pictures? How is it done? The measurement technique used for this is called Michelson contrast techniques, which is in detail more or less something that you set the focus of the camera system on the image reflected and adjust luminosity. After displaying and grabbing some fringe pattern of strong contrast, for example, this is one of the fringe patterns used for that technology, you can get a relation between the reflected fringe pattern or the projected fringe pattern and what the camera picks up. And as said, for a live picture, for example, of an orange, this could look like that. And what you can already see here are some distortions. These do not really take place for the contrast, but these are handled later. But you can see that the difference in general between a very strong contrasted scene against a low contrasted scene is more or less a grayish impression. It is a bit hard to really show real life samples in a webinar, but let's try it. So we have a lamp reflection in coated panels here, and the C value of these rank between 72 to, let's say, 86. And if we compare them side by side, the general impression that you receive of contrast is more or less the lightness that you have in the scene between part 1 and part 3, for example. So in the end, contrast gives you indication about the reflection itself. Another real-life example that we will use for our later demonstrations more is explained here. So you can see 3 samples of orange metal coating that more or less have all around the same C value. So C tells you it's more or less in the same color impression range. The influences on contrast come from the paint color itself. So if we try to rank it a bit, we can say that metallics and white will normally be found around 20 to 30 contrast values. More deep colors are around 70 C and higher, and very, very deep colors like black colors are ranked above 90. The second expert parameter, sharpness, is an indication of the detailed reflection that you have. When you take a look at a surface, it's now not the case to see, do I see a reflection? But yes, I see a reflection, but how clearly can I see it? What is the clarity of that? If we take a look at the examples below, we can see a surface with a very, very poor quality. It's a bit unsharp, as we would say, and it increases up until 95, where you can see any kind of detail in a scene. So S, or sharpness, is ranked from 0 to 100, with 100 being a perfect mirror. Well, how can we measure something like that? Again, you see here the frequencies displayed on the upper right, which are used for the measurement technique optical transfer function. And the optical transfer function is an indication of how good can the camera pick up a reflected image. As with everything, the absolute ideal surface does not exist, but if you take a look at a very high quality mirror, you could see that any kind of these frequencies displayed, so the distance between the black and the white here, are picked up, and ideally it would be 100, but as said, it's not 100 over all ranges, so the smaller or the higher the frequencies get, the more loss in pickup you would receive, but that is quite normal. If we take a look at a not so nice surface, for example, between the mirror that we just saw here, so this is the calibration mirror, for example, against a very poor transmissive surface, you can see that in the end, the high frequencies blur in together and you would not see any kind of details reflected, and that gives you this kind of surface or function. So sharpness itself is captured in this fashion, projecting the fringe images, another surface, as you can see, and this normal surface, let's call it the normal transmission, is then integrated, and the integration delivers the value S. Taking a look at our real live examples, sample 1, 2, 3, What we can see here or discern, let's say that the one in the middle gives a very nice reflecting image. You can see nice details of the lamp that is projected, which also delivers a sharpness of 98. While on the left side, it blurs, and the blurring is about 72 for sharpness, while on the right side, it's very near to sample 2, but a bit decreased. So this is seen in 94 compared against 98. What are the influences on the sharpness value received? Well, you can say that any prior surface that you apply a layer over affects the next layer. So the prior surface condition is something that affects the sharpness value, plus the curing condition. Of course, sanding has a high influence to flatten a surface, for example, the application parameters and the material as well. So high quality image reflections are normally ranked above 85. The standard detail reflection in a normal coating would normally range between 75 to 85, let's say. Then we come to something that we call waviness. Waviness is ranked from 0 to 30 typically, and is an indication about how flat a surface is. If you give several samples to a customer who has no clue about waviness, orange peel, or whatever, they will rank a surface according to the distortion that they see. So they would say, I see a more distorted image, I see a more wavy image, or I don't. And this is exactly what we're doing with the W value. The W value is the grade of image diffraction, or this is used by reflected image line deformation analysis and correlated by an Audi AG perception analysis. Here we display straight lines, either horizontally or vertically, and then grab the images. By analyzing the images grabbed, we can see how far is the line distorted from its straight line, for example. And as we have a 2D CCD sensor behind it, we can easily track which pixel is deformed in which way. So the line deformation that we pick up gets then fast Fourier transformed. And again, the result of the W is the integration of that transforming. As we said, waviness is a grade for distortion of the surface, or orange peel, or whatever you want to call it, is that you can see it here, a very flat surface, a very nice surface, as you could deem it, has a low waviness, and increasing deformation on the surface results in higher waviness values. Influences on waviness are, of course, the drying orientation. For example, horizontal parts get a less wavy surface than vertical parts. But of course, formulation parameters like thickness or viscosity, or even the substrate used, has an impact on that value. The last expert parameter we have on the TAMS is the so-called D dimension, or also dominant structure size as it's called, which is then in fact, well, which waves are, or which structures in the image, in the distortion, are most appealing to the eye. And if you take a look at that, it would be the frequency that you see in the waves. We have some simulations in the bottom again, between a very small waviness or dimension against a large structure. For this kind of measurement, we use a so-called phase measurement deflectometry, again correlated to a perception analysis. And here we project several fringe images, fringe patterns, to compute a complete curvature map. Inside the curvature map, you will of course not see only one dominant structure size or one frequency, but you will see a sum. But again, the eye is not sensitive for all of them in the same fashion. After we pick up the raw surface spectra, or everything that is inside the curvature map, we apply a so-called contrast sensitivity function for, again, the determined viewing distance, the showroom distance, again, as we call it. And by multiplying both curves, we get the weighted surface spectra with the indication which area or which frequency appeals mostly to the eye. And by detecting this dominant peak position, we get the exact dominant structure size. Well, how can we see that in the images that we've already seen between our three samples, 1, 2, and 3? What we can see when we make a close-up, of course relative in this regard, but it gives you an impression that you say, well, I can see some kind of waviness in here, but what is the frequency of that waviness in there? And that is the dominant structure size. Of course, for our small waviness in this area, the D is smaller than in the other surfaces. Here in the middle, it is much longer than in 1 and also longer than in 2.5. In the third sample with 2.5. The influences on the dominant structure size again relate on the substrate and the material, the film thickness, and the application. As we can see, substrate becomes very important in that whole structure. So this is where we talk about in the raw material mode. For now, we are finished with the expert parameters explanation and jump into the management parameters, which we call quality and harmony. Remember the surfaces we already shown in the start. Quality is a single value, as we said, that we needed, a single value answering the primary sales question. And the primary sales question is, of course, if a car stands in the showroom, is the impression that it delivers to a customer, is it a good impression or is it not? How can we judge that? As we said, a single number is now welcome to judge quality of a surface. And as long as we have one number, it's easy to benchmark different parts against, for example, a reference number. Quality is an index ranging between 0 and 100, with 0 being very poor to 100 being perfect. The algorithm used for that is based on contrast, sharpness, and waviness in a certain combination and weighting, and these three parameters delivers the final Q. And the Q is based on a correlation of Volkswagen AG quality perception studies. We said ranking, we said benchmarking, we said single number. So what does this single number show us? And as you already seen and judged by yourself, is that sample 2 looks very nice. You have a very nice deep reflection with details, less waviness, and so on. So our sample number 2 gets roughly, let's say, something above 80. Sample number 3 is not bad, but it's less quality, so it's 76. And of course, orange peel, high waves, distortions in the sample number 1 delivers a value below 50. So again, quality is one single number to benchmark the paint appearance quality of a surface or a part, and all surface colors can be controlled using a single Q tolerance. It is worthy to note, let's say, that 100 is a very, very perfectly smooth mirror surface, no haze, no waviness, no nothing. And of course, this is impossible to receive with a coating. But it's only one part of the story. So having one number to rank and bench it is very nice and very welcome. But more usage is delivered to know if I combine parts together, like let's say door to door or door to rear, what is the impression that a customer will receive? Will the eye have a so-called anchor to notice inhomogeneous surfaces, or are they okay? A part doesn't need to be 90, it can also be 70, but 70 and 70 combined are very homogeneous, while you can see that 70 and 86, for example, look very different. And this judgment is what we are doing with the harmony. As this judgment that you have just seen between parts is normally done at showroom distance around 1.5 meters, it's not so much influenced by contrast, it's not so much influenced by the sharpness, but mainly by what we call the delta appearance or the homogeneity between parts, and these are mainly waviness and dimension. Making a difference measurement between the reference and sample measurement gives us the delta waviness, and the same for dimension. And weighting and combining both values delivers the harmony or H value. Now we said for harmony we compare parts. The way that we compare parts is pretty important in order to know what the harmony is or how you judge it. And this can be followed by measurement against measurement, like in a workflow. You measure door 1, you measure door 2. What is the difference between them? Or against a global reference, whatever you seem fit or what your workflow is supposed to be. In our example here, let's say we make a measurement of sample number 1 first, then we make a measurement of sample number 2, and the difference between them is 1.8. The next measurement is sample number 3, and the difference between 3 and 2 is 0.9. One note that is important to state is that this harmony value was pushed into existing as being statistical, means a harmony value of 1 is accepted by roughly 50% of the observers. Higher than 1, less and less people will accept this kind of inhomogeneity, or below 1, there shouldn't be any problem at all combining parts or surfaces. Of course, measuring all these values is only one part of the game. It's also important to set the device up, to use the device, and also make reportings. For this kind of workflow configuration, we have an Excel-based applet that is called Smart Manager. Smart Manager lets or allows you to customize your workflow with the information in the workflow that you seem fit, that we call job, for example, which can be a model, color, process, measurement point, filler, material, whatever. So it's up to you to define what will be displayed on the device when you need that information. So pre-configurement of the database inside the instruments let you choose from predefined information stored before, like let's choose a model for the measurement, which color do you measure, what is the process that we are in, and which measurement point shall we set. Means, what did I just measure? Did I measure the rear? Did I measure the door, left, right, or the hood? And then we apply the information and we get the completely set up measurement. After you're finished, you export the values back from the TAMS into the software and can use any kind of image. For example, here we used a complete butterfly, but it can also be an image or a photograph of a door with measurement points that you can define. And not stated here, but it's possible to set several points that you measured and make a quality and harmony calculation afterwards. These measurement values can then be given out in certain setup report formats to either deliver all kind of values for all parts measured, or only Q or only H, or whatever is needed in that regard. So it's a very easy to use software that offers a lot of capabilities. We have now heard that the final quality of a surface is strongly influenced by the substrates or the layers before. So one of the tasks when developing the TAMS was to have one device that is capable to measure in all kind of production steps, like E-code, stamping of raw materials, and see the qualities inside each of these steps before they have an impact on the final quality. So how can we do that? TAMS is, as said, capable of measuring any kind of surfaces by delivering roughness parameters for any of these stages. Roughness measurements are a common tool in the automotive industry to judge surface quality of substrates. So the possibility of TAMS to measure in any of these stages is very useful. Namely, these modes are the so-called E-code mode, or KTL in German, or electrostatic coding mode, plus the raw material or RMAT mode. For both modes, we use the technology, the already mentioned technology of phase measurement deflectometry, which is the judgment of optical roughness computed from true 3D altitude maps. As we said, our measured, imaged surface can be analyzed for any kind of parameters, E-code or steel surfaces, which give a very mighty tool to optimize, for example, sanding processes or the influence on different sanding and brushing on the next layer applied. Not all of you may be familiar with that term profilometry or surface profiles or whatever, so let's have a short excursus on a profile. So what is it? If we take a very close look at the part, we can see its surface in detail. If we now turn that surface so that we look directly at its front line, what we could see is the negative, as we can call it, or the profile of peaks and valley this front line has. What a profilometric system, a stylus system, would do, that it has a sharp needle and follows the surface and give you an indication of how does the path that the needle takes over a certain length, the sampling length. And this profile received is what we call, in terms of roughness profile. From this profile, we can get various information about the surface seen. For example, the most commonly used parameter in that regard is the RA, the arithmetic average of the absolute values of roughness profile from the mean line. Means that we now mirror the negatives over the mean line and then calculate anything into the RA, or the average roughness profile. Depending on the standard used, you will find a lot of indices that are computed. For example, the RMS parameter for RA, average amplitude in the height direction. And all these kind of indices can be delivered by TAMS and the roughness profile map. So it's also important to note that there are several kinds of profiles: primary profile, waviness profile, roughness profile. Let's put it that way, that the roughness profile that we analyze here sits on top of a large frequency, normally depending on the surface, which we call also waviness for that, the waviness profile. And it's a very low frequency, and ideally it can be filtered out and allow judgment of the true roughness surface only. Yeah, so the roughness profile sits on top of a larger frequency, as we can say. By filtering out that line, we can see the true roughness the surface has. As said, roughness measurements are used at almost all major OEMs and are a very useful tool. It has some drawbacks, some restrictions, some limits that we talk about shortly, but we can come over it. Unfortunately, we cannot present more data and disclose data at this time due to OEM confidentiality, so we'll talk about it in general. So the devices used normally for true roughness measurements in an OEM are either 2D stylus systems or optical 3D interferometers, and they both share the same limitations, as they are very massive, mostly slow, and very expensive. They also come in as portable stylus profilometers for measuring substrates, but they have other limitations in terms of filtering of waviness bands, for example, and normally are limited to linear profiles only. But they all follow the ISO standard, normally 4287, which is the geometrical product specifications of surface texture profile method or line profiles. And this is what TAMS can deliver to you as well. So what we have here is the so-called optical RA or RA, which is the optically measured arithmetical mean deviation of the complete altitude map. Of course, it's possible to pick out a single line and get the profile line as you have it with a stylus system. But as we measure a complete map, it's also possible to take all lines measured and calculate the average profile out of the complete topographic map. In addition, you will receive some kind of waviness indication to tell you about the non-flecked characteristics of a surface and also a quality based on that slope waviness. What TAMS is doing, it delivers the complete topographic map as said, and this topographic map comes in open format, so it can be used with any kind of texture analysis software like Voxler or Bandify in order to calculate indices from the measurements that TAMS itself is not delivering. But using a complete surface analysis software, it is possible to get all relevant ISO indices. It's also possible to use the RoPoint Optimap Reader software that is included in the TAMS package to allow simple surface and roughness analysis, for example, profile cuts in any direction that you want, and also make defect analysis based on topographic maps. The ISO 4287 is one of the first standards for that topic. More and more the industry moves into the direction of aerial measurements, as we said, and in order to get correct readings for this and comparable readings, filtering is defined in the ISO standards, and this is ISO 16610. And the reason for filtering is to separate large and short wave components. For the TAMS, we have built in some Gaussian filters that are based on ISO 16610 standard, and you have the possibility to set up different filters for your usage. Means you can set high pass filters to keep only high frequencies, or low pass filters to keep only large waves, or a specific range that you want to analyze. How will it look if we have a look at an E-code surface, for example? You can see pictures and also filtering based on ISO definitions, which are several predefined band passes that are, as said, described in the ISO 16610. The important thing for this is that since June, it's now possible to not only use that kind of filtering for the roughness of raw material and E-code, but also in the C-code. Means you can have predefined or in the industry known parameter like short wave or long wave based on filtering that you can give out, and this makes the TAMS compliant to existing 2D scanning instruments. Based on this filtering, you can get on the TAMS GUI the information of global area roughness amplitude, or 3D-RA as we can also call it, plus the known RA in X direction, or the average linear roughness in Y direction, all at the same time, plus the mean width of the profile elements. Important to note is that the TAMS is using the whole field of view of 27 × 60 millimeter for this measurement, and it exports not only the selected bands that you have, for example, for high pass filtering or band pass filtering, but also unfiltered and filtered maps in .rs format that you can import in any kind of surface software. For example, having a look at one and the same surface measured with high pass filtering, which means we attenuate wavelengths larger than 1 millimeter, gives you the roughness profile as you can see it here. Setting the band pass filtering for the same surface gives you a different profile depending on what your needs are. So we are nearing the end of our webinar, and I want to give you an outlook what is possible with TAMS in the future, or what we are working on, like let's call it a sneak preview. So the future development can, of course, be for alternative substrates and other materials, like the analysis of carbon fiber raw material with and without clear coat, as well as interior trim materials like leather, or also in the building industry or in the plastics industry to characterize different surfaces. Of course, it's also possible to satisfy the needs for Industry 4.0, namely inline production. This is where we have RoboTAMS, and RoboTAMS is completely comparable with the TAMS portable device with a much larger field of view. With the portable TAMS as 27 times 16 millimeter measurement, the Robo TAMS offers 50 times 50 millimeter measurement, delivering the complete same results and also enabling direct onboard laser measurement for distance measurement, and many more features for your convenience. So when we deliver the TAMS, it includes a lot of standard accessories. These are namely the standard accessories like calibration plates, certificates, and so on, plus a docking station with SD card reader implemented, plus the software packages that we already named, like Optimap Reader software and Smart Manager software, and all for the suggested bundle price of 20,000 euro. Coming to the end, we will have the summary of what TAMS is, or what are the main features of TAMS. As said, the goals fulfilled, it is a static image analysis device that can deliver photos, graphs, and topographic measurements of a surface with a high correlation to human visual perception for quality control. The unique parameters, quality and harmony, allow fast and quick pass and no pass decision in production QC. The device itself is applicable to all materials, from raw material, E-code, filler, to the final C-code, whatever you need. And the ISO-compliant topographic roughness maps are delivered in standard file format, so they can be used with any kind of software already present in your company. All of this makes the device, the TAMS, a very useful feature that will find its way and will now be released in the latest VW quality specifications and procedures. At that time, I thank you very much for your attention. And as mentioned by Mrs. Bukhari, please write your questions, if you have any, into the chat or send us an email. And after this webinar is finished and you log out, you will find that there will be a survey, and we ask to take you a bit time, which will not take longer than a minute normally, to answer the survey in order to improve our webinar quality. Thank you very much. At that point, I would like to hand back to Mrs. Bukhari, which has collected the question, and we will see what we have.
Exactly.
Thank you very much.
Exactly. So many thanks to you, Mr. Dietz, for this highly interesting presentation. Thank you very much. And yeah, I think it's time now to move to the Q&A session. So let's have a look at the questions. Yeah, so this is the first one. It says, is it possible to use a topographic measurement also for the top coat, Mr. Dietz?
Yes. Yes, it is. When we, I think it was hidden somewhere before and I jumped over it a bit, but here we said that it was not, but it is since June 2020 now possible to use the topographic measurements with all kind of filtering for the clear code as well. No? This enables the correlation, for example, to existing devices for shortwave and long wave measurements to judge the common or established ISO parameters, as you can find them, not only for raw material, but also for clear code. Thank you.
Okay, let's go to the second question. There is written, can the TAMS give out wave scan indices?
Well, this is related to the same slide, so I can stay here. Yes, mainly said the wave scan are the established 2D scanning instruments that are doing a quite good job until now. So we have the possibility to correlate these values by using the shortwave and the filtering as they are set inside ISO standard. They are stated in the ISO standard, and yes, correlation is currently done, let's say.
Okay, so let me grab the third question. It's written, is it possible to use several different references for classifications?
Well, yes, it is. Going back to the beginning of the presentation is, sorry. So we talked about harmony And the harmony, as said, is either based on a global reference, so you have a master standard to compare your values against. So either that, or you make a part-by-part workflow to compare against the references. So you have the reference for that calculation is the last measurement, the reference for this calculation is the last measurement. And it is also possible with the latest firmware to set up several references, and you can have the TAMS judge between, or let's say the TAMS rank your result to say it's nearer to reference A or nearer to reference B or nearer to reference C, whatever that measurement is. So the answer, long answer is yes, it's possible.
Okay, so then we got another question saying, does this device work for measuring high glossy surfaces like stainless steel with 2R surface in brackets 800 GU at 20 degrees? How is this measuring principle comparable to a gloss grade measurement? And he added in another little message 20-degree geometry.
Yeah, that's an interesting question. Just this week, I was at the steel producing company with the device, and it's definitely possible to measure any kind of surfaces. To give you the impression, I mean, we also calibrate the TAMS on a complete mirror system, a high glossy mirror that will deliver roughly 2,000 gloss units at 20 degree. And it all depends on how you set it up. But the answer is yes, it's also possible to do that. But I guess it would also be interesting to get into contact directly to give a more profound answer to that rather large and complicated question.
Okay. So should I move then to the next question? Is that okay?
Yes, please.
Yes, okay. So next question is, can TAMS be used on sparkling base coat?
Yes. Yes, it can.
Okay. So this is it. This is your answer.
This is so the short answer first, yes, it can. And the long answer will be yes. Of course, as we said, TAMS is capable of measuring inside any of these surfaces. I guess I hid it somewhere in here, is that all surface colors can be controlled. And all surface color means that also in the tests being performed by Volkswagen at numerous sites, they were not only tested on black car surfaces, for example, but there were any kind of surfaces. And the algorithms has been fine-tuned to match any of these surfaces, be they sparkling or be they highly grainy or whatever. So it's a matter of, as we have hidden in here, let's say, the weighting and the combination of the expert parameters and how we make use of them. And it's related on contrast and it's related on sharpness as well. But yes, they can be used on that.
Okay. So then we move to the next question. This is currently linked to VW and Audi. What are the plans with other OEMs like BMW, Mercedes, etc.? Do you see this replacing the big Gartner devices?
Well, what we can definitely see is a high interest, as the TAMS can offer so much more than you can do with the current existing devices. Means we have a lot of projects and also finished projects, let's say, with other OEMs than Volkswagen that use the TAMS to get a more detailed impression and to analyze effects that are not measurable by the scanning devices. Of course, I jumped over it. Oh, I guess I had here already as well. I mean, if you have smaller parts that, like a C-pillar, okay, there's not a C-pillar, but areas where you cannot really scan the full length of a part are hard to discern with the current technology. While for the TAMS, it's image-based. You simply place it on the edge and get directly the reading on the edge of the part, and you can really compare this this location to that location, which allows also for the measurement of local disturbances to analyze characteristics or errors, surface distortions. This is the reason why more and more interest comes to us to use the TAMS, either side by side or replacing devices, let's say.
Okay. So next question is, can it be used on anodized parts and measure the color differences obtained due to different process or raw material batch? Mr. Dietz.
I guess the important word in here is, can it be used to control color differences? And as we said, we are not doing color with the device yet. So what you get is, in this regard, the contrast as an indication of the lightness of a surface, but you do not get, for example, LAB values or something, RGB values out of it to compare color of that surface. Yeah. If that is the question, if I understood that correctly. Well, it can be, to answer it also in a different fashion, is yes, we can use it to analyze anodized surfaces. We can analyze any kind of surface, from being very, very matte, like even textile, let's say, up to very, very high glossy mirror. So anodized surfaces come in between somewhere. You can do that, but not in terms of color right now. So you will not get a color indication of the anodizing process.
Okay. So another question is regarding RoboTAMS, is it commercially available and
Yes, it is.
installed at any automotive lines, and specific robot brands, or sold as a tool only?
I guess I don't really grab as sold as a tool only. I'm going forward to that slide, sorry. So the answer is yes, it has been sold, and it's also already used in production at some OEM, let's say, and also in the aviation system, where the surface requirements are very similar, but we have just started to market it. So yes, it is used, but it's not widely used, if that answers the question. Does it? I guess I lost the question a bit, sorry. So again, for any participant, if you're not happy or if deem the answer not detailed enough, please send me an email and we will discuss that off topic much more in detail.
Okay, so then should I move to the next question, Mr. Dietz?
Yes, please.
Yes. So there's D, dimension, dominant structure size. With respect to the dominant structure size, does this take into account haze, or would you expect haze to be the dominant structure? Haze being a visible structure below a high gloss finish, base to clear interface.
Yeah, I would say it's also in dimension, but it's more related into sharpness. The dominant structure size here, it's more relating into the waviness characterization. I'm jumping over to sharpness. And for sharpness, we are not giving out a haze value per se, let's say. So you do not get next to C, S, W, and D would not get an haze expert parameter, but haze is more or less something that appeals to the eye the nearer you go, and then it moves with the impression when you move away from a surface. So this is in the algorithm for the sharpness, as you can also see here. It's a reflection, and if you move the eye very, very near, for example, to the surface, the haziness will vanish, for example, and you move further away at a certain degree, you will see it again. So that kind of measurement is hidden in the yeah, I would say it's a bit split in S and D.
Okay, so there is another question regarding E-code mode, RMAT. How much input feedback have E-code and steel suppliers had in TAMS development? How to use this data to influence E-code steel substrate? Do E-code steel suppliers recognize TAMS and any specifications ISO 16610 standard?
I guess there were a couple of questions hidden in there. Let me start with the one that I remember first, is that, of course, that raw material mode and the E-code mode were analyzed together with material producers. So especially in the raw material mode, there was a lot of input coming from steel producers that are, of course, supplying the raw material for Volkswagen, for example. They had a lot of input in there, but also from other OEMs that see the TAMS as the tool for the future in terms of judging surface quality before it affects the top coat, as we said. And we have seen that for most parameters mentioned here, the prior surface and the surface roughness of the substrate and so on have an influence. And of course, if you could control that more clearly from the start, this would be a higher impact. So yes, steel producer were part of the development of the raw material, as were some E-code producers, as well as other OEMs, to see the correlation between the measurements made on raw material with the final quality. And as we also mentioned, we are not allowed to disclose any of this data right now, but I guess what we can say is this: yeah, there is a discernible correlation between the measurements that you have on any of these modes on the final quality.
Okay, so I can see there are still many questions, but I think Mr. Dietz will answer them offline later on. So everybody will receive an answer by Mr. Dietz. So many thanks for all these interesting questions. And yeah, there's another webinar in German if you want to join, and if you are interested in it's going to be held on the 2nd of July, again at the same time, 10 in the morning. Yeah, that was it. Thank you so much for that great audience, and have a nice day, everybody. Thank you.
Thank you very much. Bye-bye.